Welcome to another case study. Today I want to process this dataset of a basalt sample. It was provided by a Profex user and it was measured on an instrument configuration that is not included in Profex. So before we can refine this pattern, we need to create a new instrument configuration, and this is what I will do in the first part of the case study. In the second part, I will actually refine the basalt dataset. The instrument is a new PANalytical Empyrean that was commissioned to the Institute of Geology at the University of Bern in Switzerland a few weeks ago. Here we can see the instrument. It's a Brentano geometry with a copper tube and a 1D detector. And it has integrated optics modules in both the incident and the diffracted beam path, so all the slits and apertures can be controlled by the computer. I asked the user to send me these pictures as well as a scan of a reference dataset. This is it, a scan of the NIST LAB6 certified reference material measured with the same configuration as the basalt dataset. The easiest way to create a new instrument configuration is to start from an existing one and change it. That's easier than creating a new one from scratch. So I want to create a refinement project for this dataset first. I go to the Add Remove Phase dialog. I select LAB6. And I will pick some instrument configuration here. Maybe something from PANalytical, it doesn't really matter. Let's take an expert configuration with a fixed divergence slit, and I click OK. Now I get my refinement control file with the LAB6 structure file, and I can just try and run it. Now it doesn't look extremely bad, but still we need to modify this instrument configuration to match the Empyrean instrument settings. So I go to the Instrument menu and select Edit Current FPA Configuration. This will open the editor with my expert configuration in my project directory. And the first thing I do is I save it under a new name, and I will save it in the project directory. So I call it Empyrean because that's the instrument. 1D ER is the type of detector, FDS because it was using a fixed divergence slit with 1/4 degree beam divergence. So this describes the configuration a little bit. I saved it in the project directory, not in the instrument repository. I will move it to the instrument repository once I'm done. Now we have to change the configuration, and the easiest way to do that is to open the scan file. It's an XRDML file. We can open it in a text editor, for example in Windows Notepad. And it's kind of human readable. It's an XML format, and we can actually read the content. There's a comment section at the beginning, some sample information, and then the XRD measurement block, starting with a comment. And then we get the first instrument information, and then the configuration of the incident beam path. And this is the first value we need to know. The goniometer radius was 240 millimeters. So we go back to the instrument editor, click on goniometer, and it's already set to 240 millimeters. Next, it says the X-ray tube was an Empyrean copper, and then we get the focus type. It's a line focus with a length of 12 millimeters and a width of 0.4 millimeters and a takeoff angle of 7.6 degrees. So if we go to the X-ray tube, it's a cathode ray tube, that's correct. The spectrum is copper radiation. It says the width is 12 millimeters And then the apparent height, it says 0.04 millimeters. This is now not correct. There's a description of what the apparent height of the focus means. So it's not the true height of the target, but it's the height at which it appears when we look at it from the direction of the beam, which is at an angle of 7.6 degrees. So we have to calculate a little bit, do some math. I'm using Excel for this. We enter the true target height in millimeters, 0.4, and the takeoff angle is 7.6 degrees. Now the apparent height of the target is the true height multiplied with the sine of the takeoff angle. So this is the value we have to enter. 0.0529. Now most tubes have a takeoff angle of 6 degrees, but the same size of the target. And now you can see why we usually enter 0.04 as the apparent height. Then we go back to the XML file. That was the focus information. Next, it says there's an X-ray mirror. It's the Bragg-Brentano HT module from PANalytical, the BBHT module. It gives us some information about the angle, and so the acceptance angle and the length of the mirror. But we cannot configure this. It's not possible to configure incident beam mirrors in Profex or BGMN. But we can just skip this. Next, there is a solar slit. It's part of the BBHT module, and it has an opening of 0.03 radians. This is the solar slit in the incident beam. We enter 0.03 radians. And we have to be careful. Sometimes we have to enter half of this value that's specified in the file and sometimes the full value. We go to this description, and then there's this information. It says for Bruker instrument, divide the value printed on the solar slit module by 2. But we are using a PANalytical instrument. It says use the value printed on the solar slit module. So we use exactly what it says in the file. That was 0.03. So that's the correct value. Then next we have an incident beam mask. Actually there are two with the same ID, same opening, 14 millimeters, but at different positions. One is 171.5 millimeters from the sample, and one is 111 millimeters from the sample. We can only configure one in Profex, so we will take the one that is closer to the sample because it restricts the beam more. So 14 millimeter mask at a distance of 111 from the sample. Actual beam mask, 14 at 111. Then we have a divergence slit. It is part of the I-core module, and it is set to fixed divergence slit. The distance is 95.5 millimeters from the sample, and it is set to a fixed beam divergence of 0.25 degrees. This is the divergence slit. We set it to fixed, and we know the beam divergence. That's all we have for the incident beam path. Next, the sample, it only says that it was spinning at a revolution of 2 seconds. It is a Bragg-Brentano geometry, so also called reflection geometry, so that's correct. And the standard PANalytical sample holders are round, but with a diameter of about 25 millimeters of the sample cavity. So we will leave it at that. Next, we see the block for the diffracted beam path. Then there's an anti-scatter slit, which is part of the D-core module. It's set to fixed and again to a beam divergence of 0.25 degrees. So we select the anti-scatter slit, fixed, and just as for the divergence slit, we specify the beam divergence. Then there is a secondary beam solar slit, also part of the decor module, with an opening of 0.02 degrees. That's this one, 0.02, it's already correct. And then we have a detector, it's the 1D detector. Actually, it is not yet included in the list of detectors, but it will be part of the next release of Profex. We will find the PANalytical 1 detector. But I know that the sensor parameters is the same as for the PANalytical accelerator. If we go back here, we reach the end of the diffracted beam path. So that's all we need to know. Now we can run the calculation of the profile shape and then try the refinement and see how it fits. Okay, the calculation is complete. Now we can go back to our refinement project. But before we run it, we have to remember that we saved the instrument configuration under a new name. And our refinement project is still set to the old, the expert configuration we used at the beginning. So we have to change this name. If we go to locations and open the folder of our current project, we can see the new files. These are all the files belonging to this project. We can see the old expert instrument files we used in the first run and the new ones we just created with this dialog. Now that I changed the project to use the new ones, I can actually delete these expert files. I don't need them anymore. So let's run the refinement and see how it fits. Just a tiny little bit better than with the wrong configuration. Let's zoom in and analyze the misfits. It's mostly the intensity that's wrong, but the shape looks pretty good on the left side, but not so good on the right side. Now what I want to do to make the profile optimization a bit easier is I don't want to do a full Rietveld refinement of the LAB6 structure. It is enough if we do a Lebesgue profile fit. It's easier to see if the profile shape is correct or not. So let's close this. Let's open the LAB6 structure file. And we switch from Rietveld refinement to Lebesgue profile fit by adding Lebesgue equals 1. And we should also refine the unit cell. It is hard-coded right now. I want to refine this value. So now we are doing a profile fit, not a full Rietveld refinement, and we refine the A parameter of the unit cell. Let's try this again. And if we zoom in now, we have a good match of the intensity, and we see a little bit a mismatch on the left foot of the peak and also on the right one. Same here with the first peak. And as we go to higher values, it gets much better on the left side, but still we have this mismatch on the right side. Another problem we can see when we zoom in to this range is this little spike here. There's a little peak left of this very strong LAB6 peak. This is actually the K beta peak. If we press the S key on the keyboard and activate the spectral line cursor, we can see the lines of K alpha 1, K alpha 2 and K beta, and place K alpha 1 on the strongest peak here. we can see that at the position of the K beta line there is this little peak belonging to K beta. This is not correct, of course. We did not measure the K beta peak. We have excellent monochromatization by the BBHT module. And also we can see there's a little bump here in the strong peak. That's probably K alpha 3 satellite peaks. We can try to improve this as well. These radiation spectrum features, so K beta and K alpha 3 satellite peaks, are not part of the instrument configuration. It's part of the wavelength distribution file. And these files are stored in the Profex installation directory. Normally it's C program files Profex. And then we go to BGMN-Win. And here we find files with characteristic radiation information for cobalt, chromium, copper, and so on, iron, molybdenum. So the one for copper radiation we are using is the cu.lam file. This is what we specify in our refinement control file here with the keyword lambda. So we are specifying to use the cu.lam file for the characteristic radiation. And this is a text file with which describes the radiation spectrum as a set of Lorentzian curves. And the one for copper looks a bit different than all the others. If we look at the one for cobalt, we can see the number of Lorentzian curves used to describe the spectrum. And each column describes one Lorentzian curve, starting with the intensity, the center wavelength, and a width parameter. Now this is the normal definition of these Lorentzian curves, but if we look at the one for copper, it looks a bit different. It's parameterized. We can control the intensity by defining variables named alpha 2 ratio, beta ratio, and alpha 3 ratio. So this looks very complicated, but it's actually not. All we have to do is in our refinement control file, we can define these variables, beta ratio, and set it to 0. So now we reduce the intensity of K beta to 0. And this will make this little K beta peak disappear. And for the K alpha 3 satellite here, we can also add this variable alpha 3 ratio, and it should be around 0.05. We will optimize this empirically. Now let's try again. Let's run the refinement again. And now you can see very well that K beta is gone because we reduced the intensity to 0. And we can see here additional intensity. That's the alpha 3 satellite peaks, but they are way too strong. So let's reduce the value a bit to maybe 0.02 and run again. And now we have a very nice fit of this left shoulder that's barely visible here on the left side of the peak. Now remember, I showed that these two variables, beta ratio and alpha 3 ratio, only exist in the copper radiation file. So for instrument using chromium, iron, cobalt radiation, or molybdenum, you cannot use this. You actually have to edit the radiation spectrum in the lambda files. Now the left side of the peaks looks quite good. On the right side, we have some problem here. Also here. But to be honest, I don't know exactly how to fix this. I can only assume that it's related to the monochromator, that it cuts off pretty close to the K alpha 2 peak here. So the measured peaks are a bit steeper down here. And I don't know how to fix this. We would also have to edit the wavelength distribution file, the copper lambda file, and try to eliminate this. This is a lot of guesswork, and I think the difference is pretty small. In this dataset we can see it, but in most real-life dataset we will probably not see these differences. All in all, the fit is very good, so I think we will just leave it at that. We are almost done. There are a few things left to do. First of all, these new instrument files for the Empyrean instrument are only saved in our current project directory. So if we go there, we can see the 4 files, but they are not yet saved in our device repository. We have to copy them there, but even before we do that, there's one more thing to do. We changed the control file. We specifically added these 2 keywords, beta ratio set to 0 and alpha 3 ratio set to 0.02. This was only modified in this current refinement project, but we want these 2 variables to be applied to all new projects we create with the Empyrean configuration. And we can just edit this template file here, TPL. If we open it in a text editor, it's basically just an empty refinement control file. It starts with the sample ID, then it has an empty Verzehr variable, it specifies the wavelength. So here we control the default file for these refinement control files. So all we have to do is, if we want beta ratio of 0 and alpha 3 ratio of 0.02 to be added as a default to all new projects created with the Empyrean configuration, we just add it to the template file. That's it. Then we save this. Now this configuration is finalized. We only have to copy it to the device repository. So copy all files. Then we go to locations, device repository. And now I select my personal repository, not the one in the program files folder, because this one might get deleted when we update Profex. So I go to this one and I paste them here. Now next time I want to create a refinement project, I go to the Add Remove Phase dialog. I should find the Empyrean instrument. Now it's here. And if I create the project, I already get the 2 modifications we did because I added it to the template file. With this new instrument configuration, we are now ready to process this basalt dataset. I will do that in the second part of this case study, which will be available soon. I hope you will join me again. See you soon. Bye bye.